Hello. We are on day number 6. We are now halfway through our course. And I want to take time to thank those that have reached out to me via email and have, notified me how much of a difference this course is making. Some of you have reached out to me with questions, and I hope and trust that I've basically answered your questions. And I am really enjoying the course, and I look forward to the next coming 6 days or the next coming 3 weeks until we get to a point where we close off our course. And today, we're going to be talking about a topic that I basically encountered over the weekend when I took my son to the hospital. So we're looking at quality of service. And you're probably wondering, what does quality of service have to do, with going to the hospital? So I think Saturday night, my younger son, sprained his elbow, and it was a bit swollen. So as a young father, I took him to the hospital. We got to the hospital and we got to see the triage nurse. And there was another gentleman that came in around about the same time that I got there. And this gentleman seemed pretty sick. And the lady said to me, what, I need to just wait for me. I need to attend to the other gentleman, and then I'll come back to you. So she went and attended to the gentleman, and 5 minutes down the line, she came back to attend to me. And the reason why things happened in that manner was that my son did not have any life-threatening injuries. Yes, his elbow was sore, might have been out of position, but it wasn't a life and death kind of a situation. And I'm sure many of us have been to hospitals where you get there and they triage you, they ask you questions, how you feeling, the temperature and everything else. And based on the criticality of your illness, you are either fast-tracked to be able to go in. And whilst you're being served, if someone came in an ambulance after getting involved in an accident, there's a very high chance that they are going to get a right of way whilst you're basically waiting in the queue. And that basically summarizes quality of service, because on our networks, there are times when our networks encounter congestion, and congestion is when there is more traffic than the bandwidth that is available. And in the event that you don't have a triaging method or a method of prioritizing traffic, you then find that the least prioritized traffic, in as much as importance is concerned, is going to go first. And the critical traffic that is important is going to be hindered because of that. So when you're looking at quality of service, we are looking at how do we prioritize traffic on our network and deal with this issue called congestion. So if you look at our slide, we've got 3 pictures, and these 3 pictures basically depict the whole concept of quality of service. Now, I want you to imagine you get involved in an accident and you call for an ambulance, but because the accident happened during peak hour, the ambulance has no way of getting to the scene of the accident faster because it is caught up in traffic. And someone that you love dies in that process. Now, I know that is a very extreme example, but I'm just trying to highlight the concept that when you don't have quality of service, when you don't have something that can prioritize service vehicles over ordinary traffic, then these are the risks that you're likely going to encounter, where people are going to die before they get the service that they require. So in order to solve that problem, what did they do? They did 2 things. First thing, they came up with a car code in ambulance. But an ambulance without any marking and without any lights would be useless, because every time the ambulance needs the right of way, it then has to go and convince cars that, oh, by the way, I'm an ambulance, or there's my badge, I'm an ambulance, so give me right of way. And obviously that would probably waste too much time. So what did they do? The first thing is that they marked the ambulance with a sticker, which is very visible to everyone. And then an ambulance is then given special lights that are on top. And when those lights are on, we are all taught that you give the ambulance right of way because it is in an emergency. So two things happened. Number one, the marking of the vehicle, and number two, the classification of an ambulance versus any other car that you would basically encounter on the road. This is similar with police cars. They basically go through the same experience. Now, in the networking world, we need a way of being able to mark traffic before and during it going through our network. And we can then use that marking to be able to then prioritize the traffic. So if we see voice traffic, because voice traffic is easily impacted by delays or congestion on the network. When we see voice traffic, we need a mechanism that then allows us to prioritize the traffic as it flows through our network. So we're going to be looking at three factors that affect our traffic on our network. The first one is latency. Now, latency is the time required for a packet to travel from source to destination. So if this is our source and we're going to destination B, latency will be the amount of time it takes our packet to travel from A to B, and it is usually measured in milliseconds. And if you do ping requests on your machine, they tend to give you the response in like 200 milliseconds, 45 milliseconds. All it's just signifying is this is the amount of time it took me to get to that particular destination. And voice traffic has a limitation on how much latency it can handle. The reason being that imagine if packet number one was sent and it took 200 milliseconds, and then another packet is sent, it takes 200 milliseconds. The conversation over the phone is not going to be a smooth conversation because the packets are taking too long. So I think by standard, voice packets need about 150 milliseconds round trip, which is going and coming back. So you need to make sure that the latency is low. The second aspect that affects traffic on our network is something known as jitter. And jitter is the uneven arrival of packets. So to illustrate that, I'm just going to erase that. I'm just going to write jitter. So remember, we said A is the source, B is the destination. When the first packet takes 20 milliseconds, the second packet takes 40 milliseconds, the third packet takes 20 milliseconds, and the fourth packet takes 80 milliseconds. So this uneven arrival of packets affects the device at the endpoint that is trying to decode this information. Because when packets are arriving at a consistent time, the device can be able to time the decoding of that information. If it's a voice call, it can be able to time that whole process. When the packet then gets delayed, it forces the device to then waiting for the packet to try and figure out what is contained in that packet. And as you can imagine, on a voice call, that's going to be a moment where you're like, and then the person says, oh, by the way, I'm still there. And it is a problem when you're dealing with networks. And the last thing is congestion, which I basically highlighted when I gave us our example of our traffic scenario. Now, congestion on the network usually happens when you're connecting your router to the internet or to the WAN network. The reason being that most of the times the bandwidth between our router and either MPLS network or going to the internet usually averages about 100 Mbps. Now, if you recall, we said our network has 1 gig capacity. So each port on a switch is 1 gig capacity. and the upstream has 10 gig capability. So there's a very high chance that when traffic is going to come from your LAN trying to go to your WAN, there's going to be a bottleneck because you are coming at 1 to 10 gig capacity and you're trying to come out at 100 Mbps. And that then creates congestion. And when there's congestion, two things happen. The first thing is packets get dropped because there's not enough bandwidth to be able to then carry them. A typical case in point is you've got a hose pipe and there's too much water coming into the pipe. The pipe is going to, or you're filling up a bucket and there's too much water, the bucket is full. What's going to happen? It's going to overflow. In the process of overflowing, you are throwing away water. And in a network context, when the buffer overflows, then the system starts dropping packets. And when you drop packets, it means that an application is not going to function according to expectation. So that is, in a nutshell, what quality of service is. Now, the core focus of quality of service when you're dealing with Network Plus, and I'll say this once again, this part was not in the syllabus a couple of years back. Actually, this is CCNA, CCNP kind of content, but I'm surprised that they've included it in the Network Plus syllabus, basically trying to just help you understand what transpires. Now, there are two ways in which networks deal with congestion. There is something known as policing, and there's something known as shaping. And we're going to be talking about these two aspects. Now, policing, as you can see, we've got a policeman, we've got a speed limit. If you're driving down the road and you're traveling at more than 100 kilometers an hour and you encounter a policeman, what they're going to do, they're going to stop you because you're driving beyond the limit. And depending to what extent above the limit you're driving, they can either give you a warning, give you a ticket, or in some instances, they can actually suspend you and take away your license if you're driving 200 plus, whatever the speed above the limit. And this is similar in a network world. When you're dealing with policing, if I were to put a line, and this is the line that you should not exceed in as much as your threshold is concerned. When your packets go above, anything above the threshold is going to be dropped. That's how policing of network traffic operates. Anything above the limit is going to get dropped. So in order to prevent that from happening, they decided to come up with the method. And I'm going to try and break down the method for us to be able to understand. Now, there are two speeds that you find. There is something known as the line rate, and the line rate is the physical capability of the technology in question, right? And in our case, our line rate is 128 kilobits per second. However, there is something known as the CIR, which is committed information rate. And this is the limit that your ISP provides for your service. So when you purchase a service, the ISP says, okay, fine, you purchased a 64K per second list line. And you cannot exceed 64K, because if you exceed 64K, two things are likely going to happen. The first thing is packets are going to get dropped. And the second thing is they are going to bill you at a higher price because you've exceeded your bandwidth. Now, if you notice, the committed information rate in our case is lower than the line rate. So just because your one link out of your router is a 1 gig link does not mean that the ISP is going to give you 1 gig capacity, because the ISP gives you bandwidth based on how much you pay them. So in order to avoid exceeding this 64 kilobits per second, because if you were to send at line rate, you'll be sending at double the speed. Just because your car can drive at 200 kilometers an hour doesn't mean that you can drive at 200 kilometers an hour. The speed limit is 100 and you have to stick to it. So in order for you not to exceed the speed limit of 100, what do? You drive, when you see yourself exceeding the 100 kilometers limit, you're going to step on your brakes so that you can slow yourself down, right? And that basically goes throughout your driving journey, whatever the case might be, just so that you're not able to exceed. And in the networking world, they use the concept of buckets. And this concept of buckets is how much bits do I need to send, or the size of my bucket. And if I were to determine the size of that bucket, at what intervals do I need to pause so that I don't exceed the threshold? So in our case, our bucket, which is represented in the formula by BC, is equals to 8,000 bits, right? So if our bucket is 8,000 bits, for us to send 64,000 kilobits per second, we then need to divide the duration of a second, and a second is 100 milliseconds. And 100 milliseconds, if we were to send 8,000 at a time and pause for 125 milliseconds, it means we are going this way, down, that way, down, that way, down, that way, down. By the time we are done, we would have sent 64K per second. So the 125 milliseconds which is represented by TC, is the amount of time that we have to send and wait so that we don't exceed. So policing basically deals with the dropping of packets that exceed the threshold. The other alternative is shaping. And shaping is, instead of dropping the packets, you buffer them. Right. And what do I mean by buffer? So let's take, for example, there's a bigger bucket that is sitting here. So anything that exceeds the limit, instead of it being dropped, that data gets sent in here, and then it gets put into the buffer. And then from the buffer, as and when the link then opens up, you then forward the packets in the buffer. But as you know, the buffer cannot have a limitless size. The buffer also has its own limitations. So if you don't manage the whole shaping process, then you also run the risk that when the buffer has exceeded this limit, packets then get dropped. And in chapter 1 or day 1, we looked at the OSI, and in the OSI, we looked at TCP. And I remember I mentioned that TCP was a connection-oriented protocol, and it was one that constantly checked to make sure that the packets are being received and they're being acknowledged. The dilemma of policing is that when packets get dropped, there is going to be missing packets, and TCP then is forced to try and find the missing packets and do retransmissions in order to be able to then get the data where it's supposed to go to. And in the process, that then delays the application and causes application issues. So that is basically QoS from a network standpoint. Lo and behold, this is a very, 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 very complicated topic. I mean, it goes as far as CCIE, which is kind of the highest level of networking from a Cisco perspective, where people dive in depth on how this formula works. So I'm surprised that CompTIA brought it up to Network Plus, but kudos to them, because at least you need to have an understanding of what QoS is. The simplest, think of a hospital, think of an ambulance, think of a police car. Without any marking, without any classification, they would be delayed with congestion, and they won't be able to get to where they want to get to it on time. And imagine you have a robbery, guys are shooting and police can't make it to the location on time. It will be catastrophic. So they need to be prioritized. Same thing with network traffic. You got traffic such as voice that needs to be given priority, and this allows voice to be prioritized. There are certain elements that are not covered in this course, things like classification, things like marking, and then things like prioritization, where when the packets are getting into the network, they get classified. And when they get classified, they get marked. And then downstream, it becomes easier for us to then prioritize and implement QoS based on that. So that is basically QoS in a nutshell. And I was supposed to cover that last week, but I think we went too in depth, and it was just going to be too much of a topic. So I thought I'll just brush it aside and look at it today. And today we're going to be going into our topic of the day. We're now moving on to Ethernet. Last week we spoke about routing. This time around we're looking at Ethernet. And this is not the first time we spoke about Ethernet and said Ethernet was a layer 2. So when you're talking about Ethernet, you're talking about layer 2. And we mentioned about the category of cables. We spoke about UTP the last time and UTP distances. We are basically just continuing and now going more in depth on Ethernet. And the first concept we're going to be talking about today is something known as CSMA/CD, which is Carrier Sense Multiple Access Collision Detection. Remember I mentioned that Ethernet was, when you're dealing with hubs were one collision domain, which meant that when this PC wanted to talk, it had to listen to the wire and make sure that no one else is talking at the same time. And then it would send its packets. But sometimes you'd have moments where it might not listen correctly, and then two PCs talk at the same time. And that would lead into a collision because it's a one-way street. And now you've got two packets clashing on that. Now, when that happened, there needed to be a mechanism to try and get devices to know that a collision has taken place and to take some form of action. So CSMA/CD was the technology that was basically designed. CS being carrier sense, so the devices had the capability to sense when a collision had happened. And in the event of a collision, the devices would reset their timers. So this one would reset his timer to maybe 100 milliseconds. This one will reset his to 200 milliseconds, meaning he's going to wait 200 milliseconds before he can retransmit, allowing PCB to then send his information without being impacted. So this basically, saved Ethernet and allowed more devices to work efficiently on the network. However, efficient as it might have been, the hubs, because of the one collision domain concept, meant that this network was running at half duplex and wasn't running at its full capacity. But when switches then came into play, switches then made each port on the switch become its own collision domain. And because it was its own collision domain, there was no other device that it could collide with. And switches allowed devices to then go to full duplex. So be mindful. In the exam, they might ask you, do hubs operate half duplex, full duplex? This is what they're basically referring to. So Ethernet is basically just looking at our local area network, our technologies that are involved, the cabling that we basically deal with. And in the next slide, we're going to be looking at something that we covered the last time, which was the cabling distances, right? We said there are different types of cabling that you find when you're dealing with Ethernet. We have UTP. Oh, sorry, I think might have gone. Right, so we've got UTP, and then we've got fiber. And we say that the type of cable determines the distance that you can go and also the capacity or the throughput that you can basically carry. And we said the last time that UTP is unshielded twisted pair, which is copper, used mainly for connecting endpoints and computers. And we said that it had different categories. I think we said Cat5 was kind of like the more predominant time that UTP gained its mileage. And when you're running Cat5, which is the ordinary Cat5, the speed was 100 Mbps. But obviously, as networks then grew and technologies changed, UTP came up with Cat5e, which was capable of running 1 gig. I guess the whole aspect of this slide is just trying to highlight that the different choices you make on cabling, that's going to determine your bandwidth. This is not all of the different Ethernet standards that you're going to find, but it's just a rough summary. It is important if you're going to be preparing for the exam for you to then make sure that you've got everything else covered. I think there is a question. Let me see if I can just attend to that question. Okay, not a question. No, welcome, Fisharo. It's a pleasure that you are able to join us as we go through. All right, so I'm just going to take one step back and then erase that. So once again, I was just simply saying that the Ethernet standards, the IEEE, especially this part, because they like asking about this section in the exam. Like, do you know that 802.3a(b) is 1000 base T, or 3an is 10 gig base T? There's a lot of questions that can come out of that. Fiber gives us much longer distances. However, fiber is not as flexible as UTP, and endpoints tend to use Cat5, and fiber does not give you that option for you to connect Cat5. So just bear in mind, the cable that you choose is going to determine the distance that you're able to then run. Okay, so now this leads us to one of my favorite topics in Ethernet standards, which is Vlans. Now, I'll just draw the switch and then I'll explain why we needed Vlans and what problem do Vlans solve. So we said earlier on that this, on a hub, this was one collision domain, but when we came to switches, each port became its own collision domain. So if this was a 12-port switch, we would have 12 collision domains, each for one port. And this was fantastic, right? It helped us. However, the entire switch was one broadcast domain. Now, if you remember, I think in the last lesson, we spoke about up, right? And we said when a device connects to a switch and is trying to talk to a remote device, it needs the destination MAC address, and it goes and queries the switch. And if the switch does not have the MAC address, the destination MAC in its MAC address table, the switch is going to send the packet through every port on that particular switch, except the one that it received it from. And if that switch was connected to another switch, this would happen. And if this switch was connected to another one, this would also happen. And this is not something that is uncommon in big organizations. Why? Because I worked at a gas plant and the complex was pretty big. The corporate office was sitting somewhere located here, and the plant was about a good 3-4 kilometers down the whole campus. And I think there was another office that was sitting here. And all this was one broadcast domain. So as you can imagine, when an app request came through, the packet will be sent here. It will propagate the entire plant, getting to the switch that is at the furthest point of the plant. Why? Because it was one layer 2 domain. So VLANs allow you the ability to be able to divide. Let me see if I'm just going to try and see if I can just get a different color for my pen so that I can illustrate this point. Okay, so these blue ports will belong to VLAN 2, and then the purple ports will belong to VLAN 5. And by virtue of them being in two separate VLANs, it means that, I think, let me get the one in blue, that'll probably be easier. This one becomes its own broadcast domain. So when you were to broadcast and a packet hits here, the switch will only send its app requests only to these ports and maybe to these ports, because these are the ports that are in the particular VLAN. So VLANs, in their simplicity, basically split the switch into a logical network, and in that logical network, it then segments and allows you to be able to then divide. Now, there are so many uses for VLANs, so many use cases. You can use VLANs for security reasons, and security reasons would be, if this was, let's picture this organization as Apple, and these guys are the ones that are working on the iPhone 14. And obviously, you don't want anyone else in the organization, having access to your R&D department, because then they hold, highly confidential information and highly confidential projects. So VLANs allow you to then segment them. You might physically be sitting on the same switch, but the VLAN allows you to logically separate, and then you can put access rules as traffic goes between different VLANs. Now, a VLAN is its own subnet, meaning you can't have two computers with the same subnet mask, but in two separate VLANs. A VLAN is its own subnet. So in our case, this will probably be 192.168.0.0/24. This network will be 192.168.1.0/24. And if you remember subnetting, we said the first 3 octets, if the numbers are not identical, it means that they don't belong to the same VLAN. And in order for you to then talk to computers on the other side of the VLAN, you need a layer 3 device, either a router, or last week we spoke about multi-layer switches, which are capable of layer 3 services. So you can then create a gateway, and then you're able to then communicate going through that. Right. I don't know if there's any questions so far. I can see the numbers are increasing. If you've got any questions, this is a very important topic, one that many people sometimes find a bit challenging. And I'm going to demonstrate. Yes, I'm going to demonstrate. I'm going to do a quick lab on how to configure VLANs on a Cisco device and how we can get that going. Now, the challenge with VLANs was that I gave you a scenario, right? Because VLANs are manual, when you create a VLAN on your network, you have to go and, if you want that VLAN to be on other switches, you have to go and manually create that particular VLAN on those switches. And when you got 5, 10 switches in a network, that's not a problem. You can go and create the VLAN 5 times, and you can put computers in that VLAN. However, when you got 200 odd plus devices, sometimes 300, 400, I worked in environments where I had such quantities, right? You can't go to 200 devices and configure the VLANs on each and every device, because it's going to be time consuming. So what Cisco then did is they came up with a technology known as VTP. And VTP is VLAN tracking protocol. Let me just get my color back to the one that we're used to. All right, so they came up with a protocol called VTP. And what VTP basically does is that when switches are connected on the network and they're configured on the same VTP domain, they automatically replicate VLANs across that particular domain. So if we created VLAN number 5 here, and this switch is participating and they're all in the same VTP domain, then VLAN 5 will be automatically created on switch A it will be created on switch B without us having to make any configuration. So it basically then automates that whole process. The only challenge is that whilst the VLAN gets created on the switch, no port is configured, because configuring of VLANs is a two-step process. The first part is creating the VLAN. The second part is allocating a switch port into the particular VLAN so that you can then be able to get that working. All right, there's another question. I'm just going to take a pause because questions are very, very, very important, especially on this very crucial topic. Okay, so the question is, I use VLANs on my IDM Pro so that I manage IoT devices. Finding ports for devices like Roku players isn't easy. Okay, yeah, I guess at the end of the day, VLANs just allow you to segment, logically segment, right? Where you can't physically segment, you logically segment in the backend, and you can have VLANs basically running. All right, so I'm just going to pull up my GNS3 packet tracer, and we are going to configure VLANs, and we're going to configure VTP, and we're going to see how VTP basically works. So I'm just going to quickly see if I can bring my keyboard. And oh, sorry. I thought I brought my screen. My apologies. All right, let's erase this one. Okay, so this is just going to be a simple lab. So I'm just going to delete this, and I'm just going to bring in two switches. It's just going to be quick and simple, nothing complicated. And we're going to get these guys going. Right, and then I'm going to connect a cable between these two. Okay, whilst they're coming up, I am going to go into CLI. All right, so this is, we're going to enable, and we are going to name the switch so that we can easily identify. So this is switch number 1. Okay, host name SW1. So this is switch number 1. So if I show, just going to exit, show VLAN brief, this is the command that we type to be able to see what VLANs are configured on our switch. And in our case, we've got these default VLANs that have basically been created and nothing else. And I'm just going to minimize this, and we're going to go and look at switch number 2 and just confirm that it is of the same config. And then we're going to then configure our VLAN, and I'll show you how to configure a VLAN. And then we're going to then test VTP and see how it works. All right, so conft host name, and this is switch number 2. Okay, switch number 2, show VLAN brief. Also, no VLAN is created. Okay, fantastic. All right, so let's go back to switch number 1 and let us create. All right, let us create our VLAN. So the configuration to configure VLAN is VLAN question mark, which is the VLAN number. So you're going to configure VLAN number 10 and press enter. Now at this point, the VLAN is created, but it doesn't have a name, right? So always encourage people to create a name for your VLAN so that it's easy for you to identify it at a later point. So we're going to put name, and we're going to call this, iPhone. Anyway, we're going to call this, let's call this iPhone for lack of a better word. All right, cool. So we've created our VLAN. Let's type show VLAN brief one more time. And now we've got a VLAN 10 called iPhone. And let's balance out, right? So we create one for iPhone, we create one for Samsung. So let's say it's one company. One department manufacturing iPhones, other manufacturing, I don't have a Samsung phone, so I don't know what models are there. But anyway, we're going to call the second VLAN Samsung. So we're going to call VLAN 20, and the name is Samsung. All right, there we go. Show VLAN brief, and you got our two VLANs. So now, how do we put a computer in a particular VLAN? Now, if you notice, all the ports on the switch currently are in VLAN number 1, because that is the default VLAN. Now we want to put some ports into VLAN 10 and some ports into VLAN 20. So to do that, we go into configuration mode, interface, let's put FA 0/1, and then the syntax is switch port access VLAN 10. And that basically puts port number 1 into VLAN 10. And then we're going to exit, and then we're going to go to interface F 0/2, and we're going to run the same command, but this time around, we're going to put it in VLAN 20. So now port F01 and F02 are now in the two VLANs. And how do I know? If I come back and type show VLAN brief, you now notice that F01 is now part of VLAN 10 and F02 is now part of VLAN 20. So we've basically gone through the configuration of our VLAN, named our VLAN, and then allocated interfaces into respective VLANs. But if I go to switch number 2, remember our objective is switch number 2 should be able to learn about these two VLANs automatically without us manually. Okay, I'm getting an error from here. And yeah, we'll fix it together. We'll fix this together. But yeah, this is what you're bound to encounter on a real live network. I'm having a native VLAN mismatch, and that's another topic that I wanted to talk about, but we've basically encountered it. I'll basically explain it. So what this is simply saying is, when you're dealing with VLANs, there is, not VLAN, but when you're dealing with trunk links, there is a special VLAN that carries packets that are not tagged. I'm going to explain when I talk about trunk ports, but because it came up, and that native VLAN value must match on either end. And I'm getting an error on this one. And if I don't fix it, things are not going to work. So, right, so let's look at the error and let's try and interpret what it's trying to say. And then let's try and fix it together. So it says here, I'm getting a VLAN mismatch on port FA01 with switch 101, right? So let us look at, oh man, what's happening now? All right, let me bring this one back. Okay, so the best way that I can look at this is, I'm just gonna type show run, because I just wanna see what is the configuration on that port number. So we see F01, there's nothing configured. F02, there's nothing configured. So that port is simple. Okay, now I think I get what's happening. So let's go to switch number 1. Oh, man. Let me bring this back. Okay, I'm gonna bring switch number 1. All right, this keeps on coming back, sorry. Let me see what switch I'm sitting on. Okay, switch number 1, show run. All right, so what this is saying is it's seeing this configuration, this switch port access VLAN 10, and is not liking it. But we're gonna fix it. And that's what VTP is meant to fix. So if you go to switch number 2, sorry, my apologies. If you go back to switch number 2, and if you show a VLAN brief, you will notice that there is no VLAN, right? Nothing is there. And now we're going to configure our VTP mode or VTP configuration to allow these two switches to communicate and for the VLANs to be automatically created. And to make things a whole lot simpler, I'm going to start from switch. I'm going to start from switch 1. And the configuration would be conft, which is the normal configuration mode, VTP domain. So we need to come up with the name of the domain. And the domain, we're probably going to call it Cisco. And we are going to specify the mode for the server. So it needs two things, the domain and whether it's going to be a server, a client, or run in transparent mode. But in this case, we're not focused too much about that. That's for CCNA. So we're just going to be focused with making sure that it is a VTP server, which is, it's a server by default. So we've configured that. If we go to switch number 2, yeah, right, let's go to switch number 2 and do the same thing. Conti VTP domain, and be mindful, this is case sensitive. and then VTP mode server. All right, so that is now being configured. Give it a bit of time, and then show VTP status. Let us make sure that everything else is working as expected. And let's see, right. Show VLAN brief. Let's see if the VLANs are propagated. Okay, so it looks like that native the mismatch is having an issue. Let me configure what, just a second. Okay. I know what happened, right? So if I come back here, this port F01 is the one that I used as the trunk link to connect between switch 1 and switch number 2. And because I've configured it as a trunk link between the two switches, the configuration must match on either end. And in our case, it's not matching. So what I need to do is I'm just going to drop this link. I'm going to delete it, and then I'm going to configure it on a different port number so that I don't affect what I have done. And then we should see our VTP propagating and coming up on the other end. All right, so let's delete that. Where is my delete? Okay. All right, so I'm going to delete this link. I'm going to come back here, and then I'm just going to go for a straight through cable, and I'm going to pick port number 24, and I'm going to plug this on port number 24. All right, just give spanning tree a bit of time to finish off. And whilst it finishes off, we should be able to then come back and everything else should be working fine. And that native VLAN mismatch issue should basically be gone. All right, so that has come back. Show interface trunk. Let's see if our trunk link, okay, it's conft interface FA 0/24 switch port mode. Our trunk link should be up now. So interface trunk. All right, there we go. Our trunk link is up and running. We've got VLAN 10 and 20. That's switch number 1. Now let's go back to switch number 2. And this time around, we should have. All right, what happened now? Inconsistent port type. Man, there's so many issues that are happening and we have to fix them live. I didn't plan this lab. It decided to go upside down, but we are here to try and fix things. Show interface trunk, and the trunk link is up and running. Okay, that's fine. So trunk is up and running. Show VLAN brief, VTP mode. VTP is not working. Show VTP status. This is interesting. What am I missing? Sure. I think I should come up. Okay. Show run. Okay. Let me configure that. Conft interface FA 0/24 switchboard mode. Let me just force this to be a trunk as well. It should be fine. So trunk, show interface trunk. Okay, so that trunk link is fine. Let me go and look at interface 1, switch 1. Let me see what's happening on that end. Oh man, this is interesting. I feel like I'm dealing with the live situation. Show interface trunk. That is fine. Show VTP status. The domain name is Cisco. That's fine. The number of existing VLANs is 7. That's fine. That is no VTP mode. Okay, no, everything should be fine. The version is 1. That is okay. All right, I'm just going to give it one more try. And I think I'm suspecting that, and then this is what you probably might encounter with virtual environments. It might be a bit flaky as you are configuring. So what I'm going to do is I'm going to remove VTP and I'm going to enable VTP one more time. And I'm hoping that this time around, everything else will be able to then come up and everything else will be functioning. So let's go conft no VTP domain there. Okay. Let's try one VTP mode Cisco. All right, we'll change this to Cisco 123 VTP domain Cisco 123. All right, we'll change the domain to Cisco 123. Let's change the VTP version to version 2. And then we just go to switch number 1 and do the same thing. I'm hoping that this will probably be able to bring it online. If not, then, okay, enable form trunk because VTP domain is a mismatch. Okay, finally. So the DTPs are now talking and it has picked that up. So VTP domain, Cisco 123. All right. And then VTP version. All right, I hope this wasn't a version issue. VTP mode is still server. Okay, so that's done. Let's go and check one more time on switch number 2 and see if the trunk has formed show interface trunk. All right, that's not what I'm expecting. Show VLAN brief. All right, I guess VTP is probably acting up. I will have to come back and be able to try and work out, and maybe I might include it in the next update. But this is a typical case where things don't work out, and in a corporate environment, you expect you to fix it. I'm suspecting that this is probably something to do with packet tracer. I might have to close it and open it again just to try and get it back online. But this is how I'd basically troubleshoot if I was dealing with things in the real world. I have to check on either end just to make sure that everything else is working fine. And this is a typical demonstration that sometimes things don't go according to expectation. But anyway, very important lesson. I guess what I was trying to get to is with, let me bring back my slides. I'm just gonna minimize this guy, and then hopefully bring my slide. Okay, so I guess the part that I just wanted to highlight is with VTP, it allows you to automatically push VLANs created on one switch to another automatically, and they're basically propagated. And that leads us basically to the next step where we speak about trunk links. Now you notice when I configured the VLAN, I configured it on a particular port, and I called that port an access port. So there are two types of ports that you find on a switch. Access port, which connects to a PC or an individual device. And then there is a trunk port. And a trunk port is usually used to connect to a like device like a switch. So if you're connecting two switches together, you use a trunk port. And the reason why you use a trunk port is that trunk ports have the capability to carry traffic for more than one VLAN. An access port can only be in one VLAN at any given time, either VLAN 10 or VLAN 20, but a trunk port can carry traffic for multiple VLANs. And earlier on in the lab, I'll just bring that here. So when I type the command show interface trunk, you'll notice that this is carrying more than one VLAN. So it can carry from VLANs 1 to 1005, and depending on the VLAN that I basically have on my network. So let me just show VLAN brief something. Interesting. Okay. So for some reason, my VLANs got wiped off. Okay. I understand what happened. Let's fix it. All right. It's conft Sorry, I'll just have to come back to one more time. So let's create VLAN 10, name sales, and then exit VLAN 20, name marketing. Right, press enter, show VLAN brief. Our VLANs are there. Now, if you go to switch number 2, I think now I'm confident that I'll find the VLANs here. Show VLAN brief, and there we go. We have sales and marketing on VLAN 2 automatically being pushed without us configuring. And I remembered what happened and what caused this issue to happen. And I'll probably explain it to you. And please don't do this in production, because this is a very typical case in point where things were going to break in a very impactful manner. So remember, I had switch 1 and switch 2. And I said that I feel like something was wrong with CDP, and I reconfigured CDP. And because these two switches are running in VTP mode server, on the second part, I configured switch number 2 first before I configured switch number 1. And then I went and removed VTP on switch number 1. I changed the domain name. So switch 2 came in thinking that it was the master of the whole VTP configuration. And in the process, it wiped the database for VLANs on switch 1. And yet, when we created our VLANs initially, we created them on switch number 1. So switch number 1 then got wiped off, and all those VLANs went. So when VTP came back working, it was working, but because the database had wiped off, there was no way that the VLANs were going to propagate because they'd already been deleted. So I just went and then recreated. I was wondering, things were strange, but anyway, so now you know why it did not work. And yeah, sometimes you get to those moments, you're like, oh, okay, it happened because of this. So that is that. But I was explaining chunked ports. So let's not get digress. So show interface trunk. Now you can see that we've got VLAN 10 and 20 that are allowed to traverse our interface. However, if I allocate conft interface FA0/10 and I say switch port access VLAN, so the access is saying this port is going to be an access port that's going to be belonging to VLAN number 10. And that port will only carry VLAN 10 traffic. So if it was on a switch, let's get my pen here. If this was port number 10 and we put it in VLAN 10, it means the device that we connect on the endpoint is going to be belonging to VLAN 10. So trunk ports are used to usually connect switch to switch, but they're also used to connect servers that are hosting virtual infrastructure, because they'll be carrying traffic for multiple VLANs. So you use a trunk port so that you can carry multiple VLANs going into that whole virtual switch, and then it can then carry multiple VLANs. Yes. Now, there is a header that is used when frames are crossing the trunk link, because there has to be a way of you to be able to identify a particular VLAN, because earlier on in our example, we say this port is VLAN number 10. There could be another port that's in VLAN number 10 on the other side of the switch. So there needs to be a way to forward frames onto switch number 2, but also notify switch number 2 that I'm carrying traffic for VLAN 10. So the header that is used has space that is reserved for VLAN ID. And this is the ID that identifies a packet that it belongs to a particular VLAN as it goes through the trunk link. When it gets to the destination, the switch then strips that ID and then sends the packet in the direction that it's supposed to go. And in networking terms, we call this a tagged frame, or basically tagging. So any packet that has the VLAN identifier is tagged so that that frame, as it traverses through, the end device will know that this frame belongs to VLAN 10 or VLAN 20 or whatever VLAN it belongs to. Any any frames that traverse the trunk link without any tags, they are called untagged frames. And they pass through a special VLAN called a native VLAN. So native VLAN is a VLAN that carries frames that are untagged, and frames that are tagged are carried over the trunk link. So earlier on, we had a native VLAN mismatch. When you're connecting two devices via trunk port, the native VLAN must be identical on either side. Otherwise, you're going to have an issue and the trunk is not going to work. And I'm going to demonstrate this whilst we are watching. Let's see. Let's get back to our switch. Do show interface trunk. I just want to see what port number we're using. So we're using port number 24. Okay, so I'm going to go and configure interface FA0/24. And on this end, I'm going to change the native VLAN is VLAN 1 by default, but I'm going to change that native VLAN. So we're going to make this native VLAN 5. And I want us to go to switch number 1 and see what is happening with switch number 1. Right, now you can see, I'm just going to erase this. We can see here that we are getting an error for a native VLAN mismatch. And the reason why we're getting that error is because on switch 2, on this port going to switch number 1, we configured the native VLAN to be VLAN 5. And yet on this end, the default is VLAN 1. So all our untagged frames are now getting confused because on one end, they are told the native VLAN is VLAN 5. On this end, the native VLAN is VLAN 1. And the trunk link breaks because of that. So just be mindful when you're dealing with native VLANs and trunk links that this is bound to happen. If it does happen, just go into the configuration. So my go-to fix is come back to the switch, show run, look for port number 24, and you will see that the native VLAN is VLAN 5. And then go to switch number 1, and then do the same thing, show run, and see the configuration. And you note that here on F24, there is nothing. And that's the reason why that is happening. If you want to fix it, you can just go into interface FA0/24 and type switch port trunk native VLAN 5 to match the other side. And then we should get that error stopping, and we should probably get our interface trunk basically running. So yes, that was a very interesting practical exercise of VLANs, configuring them and things that broke, and us trying to fix what had basically broken. Right, so we're going to come back to our slide and see where we are in as much as VLANs are concerned. So yeah, let me check if there are any questions. I'll be surprised if there are no questions. Okay, yes, yeah, the best way to learn is real world scenario. And that was a very interesting one. That was a very interesting one. It caught me. I had to remember a lot of things just to try and fix it. Someone said the screen isn't visible. What do we call VLANs as layer? Do we call VLAN as layer 2 security? Yes, VLANs are a layer 2 technology. The reason being that you can configure VLANs and not necessarily implement the layer 3 part. So by default, when you segment ports on a switch, you are dealing on layer 2. So yes, they're layer 2 concept. However, we've got interface VLANs that also happen on layer 3. So they are layer 2 concept, but you can also implement them in layer 3. I hope that makes sense. Aman, I hope you're not watching from your mobile. I will try and zoom it and make it a bit bigger so that you're able to watch. But yes, thank you, Ateshi. Right, spanning tree. I mean, today it's just these are not the most simplest of topics. This is where most people stumble, and I'm going to try my best, to explain spanning tree. And if I lose you in the process, please don't hesitate. Just put your question. I will try and come back and be able to then explain. Now, on our networks, we want redundancy. Now, if you're making a journey, I mean, Australia is a very big country. Like literally, if you want to drive from one city to another city in Australia, there's a very high chance you're going to be driving 3,000 plus kilometers. Now, a journey that is 3,000 kilometers driving through the desert, it's going to be a bit risky for you to drive without some form of redundancy, right? And the most simplest redundancy that we all have on our cars is a spare wheel, right? A spare wheel is one that if you had a puncture or something went wrong, you can put on the spare wheel, drive to the next service station, and probably get it fixed. So we want some form of redundancy, but obviously you can't carry a space of taking an engine off and putting another one. It's just too hectic a process that you can't do it by yourself. So in networks, we have the same dilemma of single point of failure. If I lost one switch, what happens to the rest of the network? So what then do? We connect networks together in an effort to try and protect and create redundancy. But by creating redundancy, we then run the risk of creating a loop. And what does a loop look like? So we've got 3 switches on the screen. We'll call this switch A, switch B, and switch C. Now we've got 3 points, and as you can see, a frame can be sent this way, forwarded this way, and then this switch forwards it this way, and then we run the risk of a loop. So probably wondering, but okay, I mean, is it a big deal? This is a big deal. Like, this is a big issue in networking, and that's one of the challenges that we have with networks in as much as spanning tree is concerned, because an IP, a layer 3 packet has something known as a TTL, right? We spoke about a TTL and said it's the time to leave. And we say that there's a default value. We're going to call it 64. And for every hop that a layer 3 packet goes through, that value gets decremented, right? So if you start at the 64, this becomes 63. Next hop becomes 62. Next hop becomes 5. And the next hop, when it gets to 0, this packet gets dropped, right? Because it has hopped so many times, it gets dropped. And this dropping is a very good thing in the fact that the packet doesn't continuously exist on the network. The dilemma with layer 2 frames is that they don't have a TTL. So when a layer 2 frame happens, the frame will continually circle through the entire network up until these devices run out of resources to process. So they no longer have memory, they no longer have CPU, and the MAC address table is so corrupted that the switch does not know how to forward packets. And why is that? Remember, we say that when an app request comes through, the switch floods every port on that switch except the port that it received. So this one is going to flood all 48 ports, and then it's going to flood coming this way. This one will flood 48 ports, and then this MAC address table keeps on changing because at one point it thinks that it's learning about this MAC address from switch B. The next time it's learning it from switch C, and that flapping then causes the network to come to a standstill. I've been in situations where a spanning tree a failure has caused a network outage, like literally a network outage goes down because of spanning tree. Because of a loop on the network. So in order to curb this, they brought spanning tree. So what spanning tree basically does is it looks at these three switches, and the first thing that it does, it elects what is known as a root bridge. And that root bridge becomes the center of the whole spanning tree election. And the root bridge becomes the master of the three switches. And then it then goes and selects out of these two switches, it figures out which one has a much better priority, and then it blocks one of these links. Right. So by blocking this link, what it basically means is that it prevents a loop from happening. If a frame came from this way, it can't go back in the other direction. So it protects the network by wherever it finds a potential for a loop, it basically blocks that particular port in question. And then in that process, it prevents a loop. So how does spanning tree elect the root bridge? And the root bridge is elected not via ballot paper. No, it doesn't happen that way. It's elected through a process known as a bridge ID. And the bridge ID is equals to the priority of the switch plus the MAC address. So there's something known as a priority, which is the value that you configure on a switch that you want to manipulate to become the root bridge. By default, Cisco switches come with a priority of 32,768. So that is, if you don't configure anything, that is the default priority that you find on a Cisco switch. So all switches A, B, and C have the same priority. So priority can be used as the determining factor of which switch is going to become the root bridge. So the next thing is they look at the MAC address, and the switch with the lowest MAC address then wins this election and becomes the root bridge. Now, if we look at our MAC addresses, AAA comes before BBB, comes before CCC. So therefore, A becomes the root bridge. So switch A then becomes the root bridge. So this is now our root bridge. So the next step is every port that is connected on the root bridge is known as a designated port, DP, right? So any port that is connected on the root bridge is known as a designated port, and that port is in forwarding state. It can forward frames. So it goes and says, okay, fine, out of these two switches, which one am I going to block, right? So it looks at switch B, looks at switch C, and then it says who has the shortest path to the root bridge. So these ports are known as root ports because they are pointing to the root bridge. Now, I'm going to explain this slightly, but it's not in the syllabus. So if you're focusing on Network Plus, it's not in the syllabus, but it's good to know. Depending on the speed of the ports connecting these ports, they have a value, right? So 100 meg port will have a value of 5, and a 1 gig will have a value of 1. The lower the number, the better the cost. So if this was a 1 gig link, it would have a cost of 1. If this was 100 meg, it will have a cost of 5. So switch B then says to himself, for me to get to the root bridge, what is the cost? Or let's say this one is another one, cost of 1. So let's make it 5. If I went this way, it's going to cost me $1. If I went this way, it's going to be 5 plus 5, which is equals to $10. So it is shorter for me to go this way. And this one then becomes the root port because it's the closest to the root bridge. Switch C says the same thing. If I went this way, it's going to cost me $6, which is 1 plus 5. If I go this way, it's going to cost me 5. And thus, this becomes the root port closest to the what? Root bridge. So now it has to then decide between these two ports, which one then gets blocked. And then in this case, this port on switch C then became blocked by spanning tree. So spanning tree then blocks that port, and that port only becomes active if any of the ports, sorry, if any of these went down, then spanning tree would then bring this automatically to come back online and then start forwarding packets. And that in itself is how spanning tree works to prevent loops. So when each switch starts, it thinks that it is the root bridge. And spanning tree communicates to the switches using something known as BPD use. And these BPDUs basically carry this priority and MAC address information. So when a switch receives the BPDU, it compares its own priority and MAC address versus what it has received in the BPDU. And if it finds a priority that is lower than itself, it then says, oh, by the way, I'm not the root bridge. This is the root bridge. And then it tries to then calculate its position in as much as the root bridge is concerned. But some of these things, theoretically, we can talk. We need to see them practically. So let us come back to our topology in GNS3, and let us see what is happening in action. And I'm just going to delete this one more time. Sorry, packet tracer. Okay, sure. So now we want 3 switches. I'm just going to get 3 switches. 1, 2, and 3. So before we start, I'm just going to double click on our switch. I hope this time around it's clear. Okay, so we're going to show spanning tree and see if we can see anything. And we are told that there's no spanning tree instance because we don't have any loop, because nothing is connected to what? To one another. Now, I want you to observe something that you're going to see in packet tracer that you're not going to see anywhere else, but you can also see something similar in the live environment. Now, when I connect my cables, you notice that there's this orange light that is there, and that orange light stays for a bit of time, and you notice that it's still prevalent. I will explain what's happening at that point. And then let's connect this switch to this switch, and then connect this to that. So now we have created a potential for a loop on our network because we have connected everything else together. So now, earlier on when we typed show spanning tree, nothing came up because we had no spanning tree instance because nothing was multiply connected. So show spanning tree, and this time around, you notice that we've got some activity on spanning tree. So what are we told? We are told that, let's see, this is the bridge priority, right? So by default, the bridge priority is 32,768. But because we are dealing with VLAN 1, that 1 is added to make it 32,769. We are told about the MAC address of the root bridge. And this is the MAC address of this particular switch. So this switch is not the root bridge. Why? Because all the ports on this switch are not in designated mode. The role is not designated, meaning that it is not a root bridge. So who is the root bridge of that particular network? Let's go to switch number 2, and let's have a look at switch number 2. Right, we're going to type our command show spanning tree, and we are told that this switch is root. Now, if you look at the MAC address of this switch, it is 001. If you look at the MAC address of the switch that we looked at before, you will notice that it is 0030. So 001 won the election because it had a lower MAC address. The bridge priority was the same, but because it had a lower MAC address, it became the root bridge. So now, to demonstrate, I think let's label our switches so that it's easier for us to identify. So we're going to call this switch 1. So switch 1, as we can see, it is not the root, because it's not, all ports are not in designated state. If we go back to the root bridge, okay, let's get this going. If we go back to the root bridge, we know that all these ports are in designated mode, signifying that it is the root. And we're also told that it is the root bridge. So let's go and manipulate switch number 1 and make it the root. And how do we do that? We do that by lowering the priority of switch number 1. And we're going to give switch number 1 the priority of 4096. Now, before I get to switch number 1, I want you to notice something. You notice this orange. Let's see. You see this orange button? This orange button is basically signifying that that port is blocked. So how do I know? If you go to switch number, we're going to call this switch number 3. Enable conft port name SW3. Show spanning tree. And we're told that port F02 is not, sorry, F01 is in blocked state. So that port is blocked. It's not participating in the flowing of the network. So I just want to show you a blocked port. And we're going to look at that port later on and see if it changes when you change the root bridge. So let's go to switch number 1. And I'm going to change the root bridge, so the priority, by using this command, spanning tree Vlan 1, priority 4096. And I'm going to press enter. So I've changed the priority of switch number 1, and I've made it lower than the priority of switch number 2, which was the root. And let us look at spanning tree and see if anything changed. And you'll notice that this switch now becomes the root bridge. Why? Because it has the lower priority. And earlier on, I said to you that the switch that becomes the root bridge is a root bridge because of something known as a bridge ID. And the bridge ID is made out of the priority plus the MAC address. The switch with the lowest priority by default becomes the root bridge. If the priority is equal, then MAC address breaks the election. So spanning tree is there to prevent loops on a network, and it goes through its election on who becomes the root bridge based on that. Now, because this is now the root bridge, if we show spanning tree, you notice that all these ports are now in forwarding state because it is the root bridge. The last aspect on spanning tree is the states that the port goes through as you plug something to that particular port. And with spanning tree, the port starts in blocked state or blocking state, which is what we had on the other switch. So a blocked port doesn't forward traffic, right? So no traffic is flowing on a blocked state. When the port notices a change in spanning tree, it transitions into a listening state. And this state takes about 15 seconds, right? So it's listening on what's happening on the network. And then from the listening state, it goes into a learning state, which takes about another 15 seconds, where it is now learning the MAC addresses on that particular switch. And then after that, it then goes into forward state, where it is now forwarding traffic. So these are the timelines. And the default spanning tree used to take about 30 seconds. So when you plug in your you plug in your cable on your switch, and most of the switches, if you don't enable port fast, the port takes about 30 seconds to transition. it's going through this whole spanning tree process where spanning tree is trying to make sure that there are no loops that are happening on the network. And this is likely something that you're going to encounter in the exam because it's very important to know, and you're going to encounter that. And that's what I was trying to demonstrate when I was saying to you, if you observe this port, let's just delete this cable. Let's not switch, let's delete the cable. And then if I connect another cable, you'll see that the ports take a good 15 to 20 odd seconds whilst they're going through this phase. And if I type show spanning tree, you'll notice that it's in the listening state. And then if I type again, it's now in the learning state. And then it should, in any time now, move into forwarding state. And those are the states that the port basically goes through as it's coming. And now it's in forwarding state, right? So very important concept that slows down spanning tree and affects some of the newer devices that boot up in less than 30 seconds and need network connectivity. So in order to curb that, there's a command that we use on our switches, which is called port fast, where you're simply saying, I want my port to go into forwarding state immediately the moment it goes online, rather than waiting 30 seconds to go through that whole spanning tree process. So yeah, that's it about spanning tree. Today the chat has quite a number of questions, so let me just double check and just make sure and that no one is asking questions. I'm missing 135 lectures in the playlist. Okay, I'm gonna add them in the playlist. I think they're just not in the playlist, but they're there. But I'll do that for you after this lesson, and I will be able to get that sorted out. All right, so cool. No questions. We can not proceed, because whatever I want to cover is still on this slide. All right, so the next thing that we're looking at is link aggregation. Link aggregation. So spanning tree, good, prevents loops, but then sometimes we want to have more cables connecting to the same switch. The problem with that is that spanning tree is going to take this cable and going to block it. It's going to block it, and we can only use one cable so that we prevent loops from happening. So link aggregation allows us to bundle multiple physical cables into one logical cable. So we can configure all these and make them look like one particular cable, and we can configure it end to end. And I think the limit is about 8 cables that you can be able to unbundle. The benefit, the first one is capacity. Right, remember, if these are 1 gig ports and you've got about 48 ports and devices with 48 gig bit capability flowing through, and your uplink is 1 gig, it means that if these devices were to talk at the same time, you won't have enough bandwidth to cater for them. So that's why most uplinks are 10 gig, but still 48 gig over 10, you might not be able to then push the same amount of data. So with link aggregation or bundling of ports, it allows us to then put 8 ports together and create an 80 gig pipe to then do our uplink. The only dilemma is that you're sacrificing your physical network ports. So for every physical cable that you connected, you're using 8 cables and you're bundling them into one logical port that you can then be able to then configure as a trunk port. Now the process of of link aggregation is it's not complex, but it takes a bit of configuration and a bit of explaining to be able to do it. But this is a practical lesson, and we're gonna lab it, and we're gonna see it happening in real life. And if you can follow through, that'll be the best. The best practice is you doing the same thing and being able to get the same outcome. If you miss a step, you can rewind and have a look. So once again, I'm going to bring my lab. And what am I going to do? This time around, I'm just going to delete. I'm probably going to delete switch number 3. Yeah, I'm going to delete this guy. I want to remain with these 2 switches. Okay, cool. Now, if we come to this switch, it's our root bridge. Show spanning tree, right? So he's designated, he's the root, fine. So what am I gonna do? We want to put 3 ports, 3 cables. And I want to show you how spanning tree behaves. So we're gonna add another cable for redundancy, and we're gonna add another one. Let's make them 3. So now we've got 3 cables connecting our 2 switches. So let us see what's happening with spanning tree. If we go to switch, I'm gonna call this switch 2. Host name SW2. Okay. So if you come here and show spanning tree, you'll notice that these 2 ports F02 and F03 are blocked. So we can't use them because they're blocked. Spanning tree has blocked them to prevent loops from taking place. So what we're going to do is we're going to configure this into 1 port channel, and spanning tree is not going to block because now it's seeing it as 1 logical tunnel without any loops, but underneath we've got 3 different physical interfaces that are connected, and thus we have 3 times the bandwidth, but spanning tree won't be blocking us. So the configuration for configuring LACP, which is the link aggregation channel protocol that we're going to configure for Network Plus, is we have to go into the interface in question. So we're going to go to interface FA01, and the config is channel group, the channel port number, which is channel port number 1, and then the mode for LACP. If I do question mark, there is LACP, which is the vendor neutral, and then there's PAGP, which is a Cisco proprietary, which we don't cover here. So active simply says, I want you to become an LACP port unconditionally. So we're going to make this active, and then automatically that port bounces and comes back online. We're going to do the same thing for port number 2. We're also going to put it into the same port channel. And then the last one is going to be port number 3. Let's see, port number 3. And then we're going to put it in the same port channel. So all these 3 ports are now in the same port channel. And I'm going to say interface port channel 1, switch port mode, trunk. So I'm bundled that into 1. And then the command to double check that the port channel is active is show ether channel summary. And then press enter. And we are told that they are P in standalone mode. Okay, let's go and configure. The port channel is down. Let's go and configure the other end on the other switch, and then we can then test our port channel and see if it's working as expected. Okay, so that is this one. And then this one, I'm going to introduce a new command, which is interface range, FA0/1 up to 3. Doesn't work on this device. Anyway, let's see. Interface range should be able to work, FA0/1 up to 3. Okay, cool. So this command allows you to configure multiple interfaces at the same time. So I'm just going to say all of them, put them into channel group 1, and the mode should be active. And there we go, show ether channel summary. And now all of our ports are now P, meaning that they're now in the port channel and they're passing traffic. So let us look at spanning tree and see what spanning tree sees this time around. And we need to go to that switch number 2. And we know that we can see that the port channel is now up. When you show spanning tree, you notice that there's no more blocked ports. Why? Because spanning tree is now seeing the one logical tunnel. So this is what happened. Whilst between our our 2 switches, we've got physical 3 interfaces. Spanning tree is seeing one gigantic pipe and it's not seeing any loops. But underneath, if we lost one of these cables, the other 2 are going to continue forwarding traffic. So LACP or link aggregation allows us more bandwidth, but at the same time, it also allows us high availability or redundancy because you've got multiple ports that are basically flowing through that are not being impacted. And that is LACP/link aggregation. Very interesting concept, very interesting topic. And yeah, saved us quite a lot. I've been in environments where when you're running cables via long distances, you run them and then you put them into one port channel. And if one port channel goes down, the other one continues running. It gives you enough time to fix the problem without causing any outages. So yes, once again, I'm just going to escape and just make sure that there's nothing in the chat. If there are any questions. All right, nothing in the chat. We are going good. So yes, guys, we're not at the end. I'm just highlighting that there's quite a lot to learn from an Ethernet perspective, and I always encourage people lab up as much as you can, and that's the only way that you're going to be able to learn. As you are putting everything else to practice. There are 2 more concepts that we're going to look at on this slide, and then we will then proceed on to the next slide. The next concept is power over Ethernet. I think that says it all. The name says it all. So PoE, for those that have not encountered it, it is when you can supply power using a switch via UTP cable. The challenge is you got devices like access points, and 90% of the time, access points are being mounted on ceilings, and you can't put power points at every point where you want to put an access point because it might change and vary. So they came up with Cisco devices that could power some of these, Cisco switches that could power some of these devices using the concept known as power over Ethernet or 802.AF. That is the Ethernet IEEE standard of power over Ethernet. So in simple terms, you're getting power from a Cisco switch. The devices that get power are access points, IP cameras, and IP phones. So very important concept. You need to make sure that when you're buying some of this equipment, I've seen situations where people buy Cisco switches without factoring the need for power over Ethernet. And then when they then put them into production, they then realize, oh, by the way, this device can't do PoE. And by that time, it's too late and it's not going to meet the specifications of the business requirements, especially for IP cameras. At work, PoE, crucial point because our cameras get powered via PoE. And if PoE doesn't work, then you've got problems. Cisco switches can push up to 15 watts. And now I've seen some going up to 30 watts that they can give per device. There are different ways that you can be able to figure out that a device requires PoE. You can probably read that in the book, but understanding the underlying concept and technology, that's what it's all about. So that's all you need to know. And we're going to close off on this one by looking at something known as port mirroring. So there are times when you're troubleshooting an issue on the network and you want to analyze packets that are traversing through a particular port. And you want to use tools like Wireshark. I'm sure you probably heard about Wireshark. Wireshark is a packet analyzer. So port mirroring allows us to be able to mirror everything that's coming out of this port and send it to a port where we've got an analyzer connected to it. So we basically mirror everything coming to this port to come out on that other port so that we can then forward the traffic And the configuration to do that is monitor session, the session number, and then the source port, which in our case, this will be gig 0/0. And then the same command, but the difference is that the destination port is going to be gig 0/1, which is going to be on this interface. So anything that comes here gets forwarded on or bounced or mirrored onto gig 01, and then we capture the traffic on gig 01, and then we can analyze it and see what is taking place. You might encounter situations in the network where you might need to do this and do port analysis, and then you can do port mirroring so that you can see the traffic that's basically flowing and try and understand what is working and what is not working. That's a mouthful. Mouthful, interesting indeed. I hope you guys are finding value, and if I've missed something, please let me know, and I'll probably come back and be able to explain. So let us proceed to user authentication. Now, for security reasons, network devices stand as endpoint devices, meaning there's a very high chance that someone can come on your desk, plug in their own laptop from home with the hope to get on the network, and from there thinking that they can gain access to the organization. If you don't protect your network switches, then anyone can plug into the network switch and be able to connect to the network, which is not good. There's so many security ways to mitigate that, but the one that we're going to be talking about is user authentication using something known as 802.1x. This is a very important concept to understand. 802.1x basically says to a switch, before I can open up this port and allow your data to flow through, I need you to authenticate, right? And if you authenticate successfully, then the port activates. If you don't authenticate successfully, the port remains shut. And this is a very brilliant technology because it means that someone can bring their computer from home and plug into your corporate network and then gain access to the network. And for .1x to work, there are three components that it deals with. The first one is the supplicant. The supplicant is the device that is requesting access to the network. And this is the device that's probably going to provide the authentication details. And then there is the authenticator, which in our case, it is a switch. The authenticator takes the request that's coming from the supplicant and it forwards it to the authentication server to verify if the credentials that have been provided match. And then the authentication server then looks at its database to try and see if the credentials presented to it are correct. And if they're correct, it then sends a response back to the to the authenticator, who then opens up the port and allows for traffic to then flow through. And the protocol that these guys use is known as radius. I'm sure you've heard the word radius before. Radius is the protocol that is used to communicate between the authenticator and the authentication server to verify that a device authenticates. If you don't meet the criteria, the port doesn't open altogether. So 802.1x, very important. You will need to implement it in a production environment, especially production in big organizations where you've got Active Directory that is acting as your authentication server. You use that, and as long as the user is in Active Directory, then they can log in. If they're not in Active Directory, they can't log in. There's another aspect of MAB, but it's not covered in Network Plus. When you do CCNA, that is basically going to be covered. So if you want me to do a class on CCNA, please just leave a comment. Yeah, now we're back to the marketing on YouTube, right? If you want me to do a video on CCNA, just leave a comment in the comment section, or just thumbs up, just type CCNA. Then I know that the people want CCNA. But if you don't want it, it's fine. Don't worry much about it. Okay, so we've looked at that. The other aspect that we're going to look at is remote access. So there are two ways that you can connect to a Cisco device. You can physically connect to the device, plug in a cable, and this is known as consoling onto the device because you're physically connected to it. Or you can remotely connect to it through things like SSH, but you need to configure it. And all these are known as out-of-band configuration or out-of-band reachability, which basically means that in the event that something happens on the network, you can connect to it out of band remotely and be able to then configure that particular device. So to configure things like SSH, you need to generate crypto keys, and these crypto keys are used for encrypting traffic. The predecessor for SSH was something known as Telnet. And the challenge with Telnet was that it sent information in clear text. So if you were to sit between a conversation that's happening in Telnet, you could actually see the entire password being forwarded, and that was a security problem. So SSH comes and encrypts that traffic and protects it. But for it to be able to encrypt, it needs to create the keys that it will use for encryption. Right. So when you configure SSH, you need to generate the keys. And then when you generate the keys, those keys are then used for encrypting the traffic. So when the traffic flows between the source and destination, you'll then be able to get the traffic encrypted. So that is SSH as an out-of-band tool. Before you can configure SSH, the switch must have an IP address. You need to configure a domain name. You also need to have a host name for your switch device. And then you can generate your keys and then be able to configure SSH on the device. So configuring SSH is just for security reasons. The second step is then to configure the virtual terminal lines that you connect to, known as VTY. So you have to then go into the device and type line VTY 0 up to 15, and then the authentication, whether you're going to authenticate locally, create a local account, and you are able to then get that going. So that is SSH. And I think we're probably going to close off by looking at first hop redundancy. But before I look at first hop redundancy, let me just double check one more time if anyone left any comments to the interest or to the effect of CCNA, and if there's anyone else with any questions. Yes, do a class on CCNA. All right, so we've got one person. At least one person wants me to do a class on CCNA, so that's fine. The last topic that we're probably going to cover today is first hop redundancy. I'm just going to first hop redundancy. And previously we looked at default gateway. I think it was about the last class or the class before. And I said that the default gateway is the gateway that takes you to the outside world. And if you got a PC that is sitting here, all this is likely going to be the same subnet. And this one is going to be a default gateway, which then takes you to the outside world. Now, when we configure our PCs, we specify the default gateway either via DHCP, or we manually configure the IP address and then put the put the default gateway's IP address. The challenge, however, is if something happens to this link on our default gateway and we have no exit path going to the other part of the network, even though we could go out to the WAN this way, because our machines are hard-coded to this default gateway, they don't have a way of being able to then look to the right and find that there's an alternative gateway. So to fix this, we can either go to our PCs and change the default gateway into something else. But if you've got 5 PCs, not a problem. If you've got 100, 200, it becomes not practical for you to go to 200 machines to try and change the default gateway. And then when the default gateway starts working, you have to go through the whole process of changing them back again. So we implement a technology that is known as first hop redundancy. And with first hop redundancy, what that does is these devices are interconnected to provide redundancy. But instead of serving us the physical IP address of this interface as the default gateway, these two devices talk to each other through a protocol known as Hsrp, and they present a virtual IP address, right? So you got, if this was 192.168.0.1 and then 192.168.0.2, instead of us pointing our PCs to either of these physical IP addresses, we are given a third virtual IP address, which is 192.168.0.3. So we then configure our PC's default gateway to 192.168.0.3. And this virtual IP address behind it is being fed by the two physical IP addresses. And one of these routers then becomes active and the other one becomes standby. And the router which is active is the one that all the traffic is going to be forwarded through because it is the active router. But we are pointing to the virtual IP address and the virtual MAC address. And if this router goes down, our virtual IP address doesn't change because it's still pointing to a virtual IP address. This then becomes the active router, and then all the traffic starts getting forwarded through this router to go to the outside world. So, and when this guy comes back online, the back end can change, but the front end never changes. So I'm just trying to think what example can I give that probably illustrates this in a more practical way. Maybe Netflix has got multiple servers, right? And then we have a CDN, that is a virtual CDN that we connect to. We are being served by the CDN. And if any of these devices fail, because we are pointing to the virtual CDN, we can still watch our content, but in the back end, the servers that might be serving us are different. We spoke about load balancing, I think in the last lesson. Similar concept, works in a similar manner. So Hsrp is the protocol, and when you're running Hsrp, you got at least two devices. Only one device can be active at any given time. The other device is in standby mode. And when one device goes down, the other one takes over. And when it comes back, it preempts and it basically continues. So first hop redundancy protocols, very important topic when you're dealing with redundancy, it's probably going to be, our last slide for the day. When we meet on Thursday, we're going to be looking at wireless concepts. Yes. So we spoke about routing. Today we spoke about Ethernet and Ethernet technologies. We're going to be looking at wireless, and then we start progressing into network operations. We were now looking at just a second. All right. So seeing that there are more people that are in the class today, that's fine. Let's proceed. Let's look at wireless networks. And okay, that's fine. Right, there we go. All right. Let me just run that. Let's get that going. Okay. All right, so we're going to look at wireless networks. So it's not too much a topic that is basically covered. So we're just going to go through the detail of what is covered in wireless. And then when we meet the next time, we'll probably focus on something else. So we looked at networks being physical, right? We have a switch, and then we've got a cable. Cable is connected to another switch, and then from the switch, we've got a PC, and that's going through. That's one form of network, which is the wired network. The wireless network, there's no need to explain. It's clear and straightforward. It's a PC connected here that is connected wirelessly, and it communicates, and it will communicate to an access point. Access point then connects to the switch via cable, and it provides the back end. This is known as a basic service subscriber, or BSS. There is also another type of wireless where you got a PC connecting to another PC together wirelessly, and that is known as an independent BSS, right? Because you don't need an access point in order for you to communicate. And then the third type, so the first one, the second one, the third type is known as an ESS, which is an extended, enhanced subscriber set. And this is where you have a network with more than one access point, right? Broadcasting signal this way, and then you've got PCs being able to then communicate. So when you're dealing with wireless networks, these are the three types that you're likely going to encounter. Now, when you're dealing with wireless network, there are challenges that you encounter, such as interference. Wireless networks are susceptible to interference, and the interference could be from multiple locations. Let me just get my slide right. Okay, cool. Right. So the interference that you encounter with wireless networks is because there are other frequencies that operate in this wireless space. The two most common wireless frequencies are 2.4 gig and the 5.0 gigahertz range. These are the two frequencies that we can use for wireless services without needing to register for a license to be able to then perform, to be able to own this particular frequency. Other frequencies are licensed. So you got frequency for police communication. If you work near airports, there's a frequency for airports, and sometimes if they need the frequency spectrum, you are supposed to, turn off your devices and give them priority because they need that particular frequency spot. So the two most common ones are 2.4 and 5 gig. These are the licensed bands that you and I can be able to then use. Anyone can make devices in that particular space and be able to use them. Once again, wireless is affected by interference, and interference comes from other microwave signals. It also gets affected by just general microwaves that you find in office spaces. They are also affected by physical obstacles. So when you're dealing with wireless networks, you need to be able to factor in things like concrete blocks that might be in your office or concrete walls, because sometimes wireless signals can't penetrate and go beyond. So if you place an access point, you might not get coverage in a different location because of these obstacles. So you need to then do a survey just to make sure that you have a full understanding. So when you're dealing with wireless, you probably go to a location and you can map out and do a site survey, and that survey will then tell you the things that you have to then be dealing with. So this could be a concrete wall. So as you're placing your access points for good coverage in that office, you need to then be strategic on where you place them. So these are the things that affect wireless networks. Let me just take a sip. All right, so these are things that affect wireless networks. On the wireless side, you got different types of antennas. And depending on the type of antenna, it determines the coverage that you're going to get. And it also determines the distance for your coverage. And the two common antennas that you find is the omnidirectional. And an omnidirectional access point propagates its signals going. So this will be the access point, and it sends its signals 360. Anyway, okay, I think might have. Okay, I think I might have been erasing. All right. Okay, so an omnidirectional sends signals in a 360-degree pattern, and you usually find them on the ceiling, and they propagate in a circular manner, giving you much bigger coverage. However, the angle of an omnidirectional going down, if this was the access point, would look something like this. So if you're not careful, these are blind spots that are basically not covered. So the first one is omnidirectional. The second one is a directional antenna, and these are usually used for point-to-point links between buildings. So this will be your, I'm sure you've probably come across the ones that look like a radar for a police car, or back in the day when they're trying to catch you for speed, they'll shoot like a radar in your direction that looks something like an aerial for a TV. And that one, you are focusing your signal on one particular point. And because of that, you can go long distances. I have set up the Ubiquity Unify point-to-point access points, and some of them have got capability of running 50 plus kilometers as long as they've got line of sight. So line of sight is important when you're dealing with directional antennas. So the type of antenna is going to determine the coverage for your network. Now, when you're designing your network, you got to factor in something known as interference. And then later on, we're going to look at the wireless standards. But when you're dealing with 2.4 gigahertz, 2.4 gig, you have a limited number of channels that you can use. And I think the channels are about 14. So 1 to 14. And the channels go something like this. And there are few channels that you can use without anything that is within the spectrum. If this is 1 up to 5, if you use 2 access points on the same channel, you're going to have interference. So I think on the 2.4 gigahertz spectrum, you only have 3 channels that you can use without interference, and that is 1, 6, and 11. So when you're designing your layout of access points and the channels that you're going to use, this information is very important. So that's the first thing, the channels that you're going to select. The second one is the coverage of your access points. Your access points must overlap. So this is AP1, AP2, AP3. Your APs must overlap so that there is enough coverage for something known as roaming. And the best way that I can explain roaming is you are working in the city, right? You're working in the city, and this is your house. And between the city and your house is about 20 kilometers. You get a phone call on your mobile phone whilst you're leaving the city, right? And in between your destination, between your house, you got base stations, right, that are propagating wireless signal. You got base stations that are propagating wireless signal. Now, the normal expectation is that your call should hold from here all the way to what? To your house. If the network coverage in that area is what? Is pretty good. But in the process, you are being handed over from one base station to another. And that process is known as roaming, because you're moving from one station to what? To another. And the only way roaming can take place is if there's some degree of overlap between the two base stations or antennas or access points. That's the same thing with access points. You need at least about 15-degree overlap or 15% overlap between your access points to allow for that roaming to take place, and anyone who's using the network to be able to then cross over and be able to then go through. And we're probably going to close off wireless by looking at security. Wireless is susceptible to security because the reach of a wireless network goes beyond our physical office building boundaries. So you need to then protect your wireless network. And I'm sure for us, for many of us, we have heard about pre-shared keys, or when you go to someone's house, like, hey, can you give me the password for your Wi-Fi? What we're basically referring to when you're saying give me the password for Wi-Fi is something known as a pre-shared key. A pre-shared key is a key that is configured on the wireless router on the SSID, and that acts as some form of security to deny people that are trying to get onto the network without authenticating. But the challenge with pre-shared keys is that they're very good for home networks, but they are not practical for corporate environments, because imagine you have 200 people in the organization. You give them a pre-shared key, and the pre-shared key is Cisco 123. And then 5 days down the line, John leaves the company. Right, he resigns. What are you going to do? Change the pre-shared key and then give it again to 199 people. And then when someone else leaves, then you can't practically keep on changing the pre-shared key. So the better way is using 802.1x, which we mentioned earlier on. And why do we use 802.1x? Because we have an authenticating server that we can then go and verify. So people can then use their own AD credentials to then log onto the Wi-Fi, and we can then be able to authenticate them in that particular manner. On the wireless side, it has also gone over different technologies to protect the wireless signal that is basically flowing through. And when we meet on Thursday, I'm probably going to go into detail covering things such as WEP, WEPA2, to understand how these technologies function and how they protect our networks. So on Thursday, when we meet, I'll basically be able to cover on that one. Before we do that, let me just minimize, come back to the page and just try and see if there are any other comments and any questions. All right, let me make myself full screen. So yes, that brings us to the end of today's lesson. I am going to make sure that all the lessons are put in the playlist, so that when you watch the playlist on YouTube, you'll then be able to see the other classes in one particular location. But once again, thank you for taking your time. I really find joy in doing these classes. And if there's anything else that you want me to cover, practice exams, if you want us to cover practice exam, just let me know. Either put a comment or send me an email later. And in what manner do you want us to cover practice exams? For those that are preparing to write the exam, do you want us to just go through an exam, 80 questions, and then explain the answers and why answers are right or wrong? Is that the way that you want to do it? Or yes, anything along those lines? don't hesitate to let me know. So guys, once again, thank you for taking the time to watch. And I will see you on Thursday.